Hello everyone, I'm Ali Reza, and today I'm going to present InfAdapter, an inference serving system that reconciles high accuracy, cost efficiency, and low latency.
More than 90% of data center compute for ML workload is used by inference services. ML services have strict requirements. For instance, they have to be highly responsive,
They must be cost efficient, and they should be highly accurate to be able to get proper results. But that's not the end of the story because these requirements are not only strict but also conflicting. And dealing with these systems is even more difficult because the workload has a dynamic nature.
over the past few years, two main approaches have been explored. First, resource scaling. Second, quality adaptation. For resource scaling, people mostly interested in improving one machine to achieve higher performance, or they adjust the number of machines in a cluster of nodes in order to achieve high performance. In quality adaptation, however, people are more interested in switching models towards lower or higher accuracy.
Resource allocation for these systems is a big problem because most of the time you end up with over provisioning or you end up with under provisioning. Let's briefly go over two simple scenarios where we show how resource allocation can be problematic and we end up with over provisioning or under provisioning. In this figure, we see time and workload demand on the y-axis. And as you can see, workload is dynamic over time. The right figure shows what is the resource allocation over the time. And as you can see, this is a static resource allocation given different amount of time. In the first half of this figure, we see that the workload demand is significantly higher than what we have allocated for this workload. This is what we call under provisioning scenario, and it leads to latency SLO violation. In the second half of this figure, we see that the workload demand is actually less than what we allocated. So in this scenario, we are facing an over provisioning scenario where we waste compute resources.
Quality adaptation is another direction on top of resource allocation. In this figure, you can see that ResNet 18 detects a tiger, and ResNet 18 is a less accurate model. On the other hand, ResNet 152, which is like a higher accuracy model, detects a dog. At the end of the day, what matters is that what accuracy you want and what level of service you exactly need.
The question is, what is the best scenario? The best scenario is where you can adapt your accuracy based on your workload. As you can see in this figure, when the workload is high, you can pick a less powerful model and achieve lower latency. At the same time, you can achieve higher throughput because the workload is high and you want to sustain higher throughput, but you cannot do it with a powerful model. On the other hand, when the workload is low, you can pick a more powerful model so you achieve higher accuracy and at the same time sustain the throughput that you want. The question is there a solution to this problem? We believe InfAdapter can solve the problem because it's a latency SLO ever, highly accurate and cost-efficient inference serving system.
Let's see why InfAdapter can solve this problem real quick. In this figure, we have two model variants, ResNet 50 and ResNet 152. The y-axis is the sustained throughput. As you can see, ResNet 152 with 20 CPU cores achieves almost the same throughput that ResNet 50 achieves with 8 CPU cores. The difference here is about 60%. So with 60% different CPU allocation, you can achieve almost the same throughput at the cost of lower accuracy. So in conclusion, you can see that by sacrificing some accuracy, you can achieve the same throughput.
This figure demonstrates that using multiple model variants in aggregate achieves better accuracy loss compared to a scenario where you have a single model. In this figure, InfAdapter uses multiple models, but model switching is fixed and just uses one model. And this figure demonstrates that accuracy loss is significantly lower when you have particularly larger amount of CPU cores allocated. Using multiple variants are interesting, but let's see how InfAdapter achieves this. InfAdapter benefits from a dispatcher that dispatches requests among the model variants. The thing is, it first has to pick a bag and select what model variants it has to use. Second, it has to load balance these requests among these variants. And this thing is done by predicting the workload. InfAdapter achieves this while it maximizes the accuracy and minimizes the cost.
In this figure, we see a monitoring component that monitors the request per second relevant to each model variant and eventually sends its traces to other components.
There's another component called adapter that actually gets fed by the monitoring traces. It uses the monitoring traces to make decisions. Let's see how InfAdapter formulates this problem. It tries to maximize the accuracy and minimizes the resource cost. First component in this formula is related to maximizing the average accuracy. And the second part minimizes the resource and loading cost of each model. So InfAdapter considers loading cost and the resource usage when the model is running. However, this formula is subjected to a couple of constraints. First of all, it has to sustain a particular load that is predicted by our predictor. Then it has to guarantee an end-to-end latency for every single request. This figure demonstrates the overall architecture of InfAdapter. First of all, we have the dispatcher, and this dispatcher dispatches the requests or load balances the requests among multiple model variants. We have our monitoring component that constantly monitors the entire system. At the same time, the adapter that runs the model, the resource allocation and model switching model, queries this monitoring and makes new decisions. And these new decisions are going to be applied via our API server. And this API server basically applies and puts or picks new models or replaces models or this stuff.
Let's get straight into the experimental methodology of InfAdapter. We use a Twitter trace for our raw data. We use Kubernetes VPA and an adapted version of model switching. So the difference between model switching and adapted model switching is that the adapted model switching is able to adjust the resource allocation, whereas the model switching, the traditional approach, just switches the models. The difference between InfAdapter and model switching plus or adapted model switching is that InfAdapter has a bag of model variants, but in model switching we only can change to one model type. We use different variants of resident 18 to resident 152. We use 30-second interval adaptation periods. And also we have a 3-node cluster where we use one machine or one virtual machine that sends the workload, generates the workload, and we have 2 other machines for our model serving system. We would like to understand if we can predict the workload because we would like InfAdapter to be making decisions proactively rather than reactively. Now, we used a LSD model to predict the workload. And as you can see in this figure, our predictions are quite precise.
Let's see how InfAdapter performs regarding the tail latency. We measured 99th percentile of the tail latency to see what is the performance. In this figure, you can see time and 99th percentile, and in 600, you can see there is a peak in our workload. And since VPA 152, it has a fixed model and it needs more, and it simply cannot sustain the throughput. That's why we have a shoot up in our tail latency. Clearly, VPA 152 is not suitable for this workload. Let's pick a less powerful model. As you can see, less powerful model achieves a better latency when the load is low. And once we have a peak, we still have the same problem because this is too much for this model as well. Now, if you pick VPA 18, which is the easiest model possible, then you can see the violations is not that much anymore. When we have a peak, the model can sustain throughput given our latency requirements. Model switching plus is another approach that we use in our evaluation. As you can see, if we can change our models, we can achieve higher. We can sustain our throughput at the same time. We can achieve the low latency. As you can see, InfAdapter uses a more powerful model initially when the load is low, and when the load is high, it uses less powerful models, and it achieves and sustains. First of all, it sustains the throughput and it achieves the SLO latency. But the comparison between model switching plus and InfAdapter is that InfAdapter uses a combination of workloads, combination of models, and achieves higher latency and accuracy compared to a scenario where we have model switching only. Let's see how InfAdapter performs regarding the accuracy. As you can see, when the load is low, there is no problem, then the accuracy loss is not much. But when we have a higher load, then InfAdapter sacrifices the accuracy and achieves, first of all, meets the SLO. Second of all, it sustains the throughput that we want. Whereas this is not possible when we have fixed amount of resource allocation, or we cannot have a combination of model variants. So let's look at the cost of the InfAdapter. Initially, the cost is high because the model does not know what's going on, and it immediately reduces the cost because the load is low. And as we go on, and in 600 we have a peak, then what happens? InfAdapter tries to allocate more resources to be able to achieve or sustain the throughput. And when the load is low, then it takes away the CPU cores that it has allocated before. Now, inference serving systems should consider accuracy, latency, and cost at the same time. Also, model variants provide the opportunity to reduce the resource cost while adapting to the dynamic workload. Also, using a set of model variants simultaneously provides higher average accuracy compared to having one variant. An InfAdapter uses these opportunities to achieve higher accuracy and lower cost, and at the same time meets the SLOs. InfAdapter is open source, and please find it here, and also please check out our paper for more. And with that, I'm going to end this presentation.